Hello, everyone. Thank you for joining us this morning. My name is Cole Wright, and I'm joined by Alex DiPetrillo and Victoria Eno. Throughout this semester, we've had the pleasure of working with the global, multinational electronics and engineering company, Bosch, the brand invented for life. They employ almost 400,000 people and have an annual revenue approaching $85 billion. Although their core products are automotive components, they do offer consumer goods and building products as well, some of which are household appliances, power tools, security systems, and thermal technology solutions. The Thermal Technology Division has chosen to support our Capstone project this year. Among other things, they specialize in boilers, water heaters, and the focus of our project this year, heat pumps. At this point, you may be wondering why are computer and electrical engineers working on a product from an industry possibly better suited for mechanical engineers? Well, we're working with the inverter ducted split air source heat pump and the CDI series SM geothermal heat pump. Now, the simple explanation to that question is among the mechanical components fundamental to all of these systems, like compressors, evaporators, and condensers, these systems have evolved to include many more other components to provide better heat transfer, more efficient heat transfer, and also electric and software components like logic boards, processors, and many sensory devices. So these systems employ a lot of bells and whistles to make them the efficient and reliable products that they are. So Bosch has asked us, and so since Bosch is a name synonymous with quality, and they're committed to developing reliable products, they've come to us and asked us to help identify why and how components fail, and in turn predict those failures and remove those potential vulnerabilities, and ultimately propose solutions to extend component life. And we intend to do so, helping Bosch continue to make certain that they are the brand invented for life. And with that, I'll turn it over to Alex.
Right, so being computer and electrical engineers, we were not too familiar with the mechanical system of the refrigeration cycle. So the first thing we decided to do was to learn about the refrigeration cycle and some of the different HVAC components. Throughout our research, we were able to determine what types of sensors we would use and what the best placement for these sensors would be inside of the units, because these are very big units. So after we determined the types of sensors we wanted to use and the sensor implementation we want to use, we were able to determine what type of microcontroller we want to use. We decided to settle on Arduino. So for the semester, our main deliverables were a hardware specification, which details how we plan to extract the data and how we plan on sending this to the microcontroller. Our next deliverable was a software specification, which is a blueprint for how we will extract the data and how we will act on the data in our microcontroller. And finally, our last deliverable was a bill of materials, which is a list of all the parts we will need to build our system when we receive our units in the spring. So our best anticipated outcome is a prototype hardware-software system composed of sensors connected to the HVAC unit, sending data to the microcontroller, which will do all of our processing. We'll also have an LCD interface, which the user will be able to view data directly on the HVAC unit. And we also have a connected computer, which will allow for some real-time and more complex calculations. Doing all this, we will be collecting validated field data to find out what is causing some of these different components to fail and when they fail. Once we have collected all of this data, we'll be using this to develop test cases so that we can test these units in a controlled environment. Now I'll hand over to Vicki.
So this is really the fundamental understanding of everything we've worked for this semester. Here we have a diagram showing a typical HVAC unit as well as all of its fundamental components and their respective sensors that we have determined throughout this semester. We will be placing temperature and current sensors on the fan, compressor, and blower up here. as well as temperature and airflow sensors on the evaporator and condenser. We'll also be placing an airflow sensor inside the filter and a pressure sensor in the inner tubings of the mechanism. We also intend to have all of these sensors interconnected and hooked up to an Arduino Leo, which we have determined will best suit all of our needs. So, as was aforementioned, this semester has really been dedicated to research and preparation for all of the work that we'll likely be doing next semester when we receive the 2 units. So we do still have some remaining challenges ahead of us, namely building a hardware system, developing test cases, implementing a software system, and analyzing the received data. So the hardware system will essentially be the infrastructure of sensory devices that I had mentioned in the prior picture. This will accrue a lot of field failure data for us, such as temperature, runtime, current, and voltage. This data will be logged and recorded on the Arduino Leo for further processing at a later time. Next, we must develop test cases to measure and verify the hardware and software of the system that we have built. Essentially, we will use these test scenarios and develop different test cases to test a certain fundamental component in the system to verify that our hardware and software is working properly and accruing accurate data for us. Next, we must implement the software system. As was mentioned before, this is going to be an Arduino-based code to record and display the data on either an LCD display or on a web interface. The main important thing here is that it must be capable of handling data from all of the sensors inside the HVAC unit, so it needs to be robust enough to handle and log all of that data. Lastly, we must analyze the received data by devising an algorithm to predict when a failure is about to occur. This is the main crux of our program, and if we're capable of doing this, this will really help engineers gain a better understanding of why components fail so that we can contribute to Bosch thermotechnology and make a more robust HVAC unit. So of course we have many people to thank for where we are today, namely Jerry Houston and Mike Kanager, our 2 technical directors. They have been incredibly accepting and understanding of all the work we've done for them this semester. We'd also like to extend a special thanks to Mike Smith, who has really given us a lot of technical help in this field that we were first unfamiliar to. Without him, we wouldn't be nearly as confident as we are today. And of course, we would like to thank Dr. Sunak for giving us the opportunity to be here and work with Bosch Thermotechnology. Thank you, everybody.